So, question 2, the first part is an example of where I would recommend giving a more detailed answer that is given in the marks scheme, especially as this is an old specification mark scheme. So the mark scheme just says that a covalent bond is a shared pair of electrons. Well, obviously, if that was the case, those electrons would repel each other, and therefore the covalent bond would be incredibly weak. But we know that covalent bonds are quite strong, and therefore there has to be an attraction between those negative electrons and something else, and those shared pair of electrons are attracted to the parent nuclei, which obviously contain protons and are therefore positive. So there's attraction between the shared pair of electrons and the distinct parent nuclei from the molecule. Okay, if we're looking at a dot cross diagram for ammonia, it's showing the outer electrons only. We need to know that nitrogen's in group 5, so we'd have 5 outer electrons. Hydrogen's in group 3, so we'd have 3 outer electrons. There are 3 hydrogens and 1 nitrogen, so nitrogen is my central atom, and I have 3 overlaps. As there are 3 outer hydrogen electrons and 3 overlaps, that means 3 divided by 3, I can have 1 hydrogen electron in each overlap. I'm using dots to represent the hydrogen electrons. As there are 3 overlaps and 5 outer nitrogen electrons, that means I can have 1 nitrogen electron in each overlap and 2 left over. And I'm using crosses to notate the nitrogen's electrons. So I end up with this diagram where I have 3 overlaps. In each overlap, 1 cross and 1 dot, and then 2 spare electrons or 2 lone pair electrons on the nitrogen. You should notice that the maximum number of electrons that hydrogen has is 2, so each hydrogen shell should have 2 electrons, and they do. The maximum number of electrons that nitrogen can have is 8, so nitrogen shell in total has 8. The 2 from each hydrogen, that's 6, and the 2 left over, that's 8. So that's a simple way of checking that you've not made a mistake when drawing your dot cross electrons, because for hydrogen, the number of electrons in that shell should add up for 2, and for any other element, the number of electrons should add up to 8. And the second part of the question, you're asked to work out what the likely shape would be of the ammonia molecule and why it has a bond angle of 107 degrees. Well, as you can see in the molecule, there are 3 bonding pairs, set 1, set 2, and set 3, and there's 1 lone pair. That makes 4 electron pairs in total. Okay, the ideal shape is a tetrahedron, because that's the way that we can put the electrons as far away from each other as possible. Okay, and obviously the electrons are going to be negatively charged, they'll repel each other, they want to be as far away from each other as possible. So in a tetrahedron, I can have a 3-dimensional arrangement. So my bond angle between the electron pairs can be 109.5, whereas if I had a 2-dimensional, obviously the maximum angle I could have between my electrons would be 90 degrees. And obviously 109.5 degrees is a bigger distance than 90 degrees and therefore preferable. However, the actual angle in the question is 107 degrees, and the question is why? Although I have 4 electron pairs, and ideally I would therefore be tetrahedron, the electron pairs are not of the same type. I have 3 pairs that are involved in bonding, and 1 that is not involved in bonding, a lone pair. And I know that lone pair repulsion is greater than lone pair bonding pair repulsion, which is greater than bonding pair repulsion. Okay, so in this example, I have bonding pair repulsion between the bonding pairs, but I also have lone pair bonding pair repulsion. And each lone pair reduces the bond angle by 2.5 degrees. So because there's 4 electron environments, there is an ideal angle of 109.5, but because there is 1 lone pair, that reduces the angle by 2.5. 109.5 minus 2.5 is 107 degrees, and hence why the bond angle is 107 degrees. If we are looking at the dot cross diagram for the ammonium ion, I can just start off with that starting diagram I had for the ammonia molecule and add one extra overlap. Okay, so I need to work out what goes into that overlap. So I started off with NH3, I've added something and I've made NH4+. So what have I added? I've just added an H+. H+ is the same as a proton, so it therefore has no electrons. So I've got 4 overlaps. 3 overlaps will contain 1 hydrogen electron and 1 nitrogen electron. And one of the final overlap will contain 2 nitrogen electrons. So if I put that all together, I end up with this molecule over here. Again, I need to check that each hydrogens have 2 electrons in their outer shell, and they do. And I need to check that the nitrogen in total has 8. So 2, 4, 6, 8. And you'll notice that because both of these electrons have come from the central atom, that is an example of a dative covalent bond. In part B, it's asking us to explain why the ammonium chloride will conduct when it's dissolved in water, but not when it's a solid. So immediately, the fact that it conducts when in solution, but not as a solid from our GCSE, should tell us that we've got an ionic compound. Okay, so when we look at ionic compounds versus covalent compounds, at GCSE you learnt that ionic was metal, non-metal. However, ammonium chloride, ammonium is not a metal, chloride is a non-metal. So it is true to say that if you have a metal and a non-metal bonded together, that would be ionic. However, there are other species that will also be ionic that are not necessarily metal, non-metal, of which ammonium chloride is one example. HCl, hydrochloric acid, would be another example. So we've got, in our bonding, we've got a spectrum. So we can have something that's pure covalent, so bromine, because there's no difference in electronegativity. Covalent, but polar covalent, because there is a difference in electronegativity. Polar, but covalent, and more polar than HCl, so such as water, because the oxygen is more electronegative than the chlorine. And then as we continue to go up the spectrum, we eventually end up with ionic. So ammonium chloride is one example of an ionic compound, and therefore the ions will not conduct electricity when solid because they'll be in fixed locations, whereas when they're in the solution or liquid state, they will be free to move. And the final part of the question is asking you to write a balanced equation for the reaction that could form ammonium sulfate. So you'll recognise from the next part of the question that ammonium sulfate is an example salt, and that is produced when an acid and base react together. So an acid is something that can donate a proton, and the base is something that can accept a proton. So you'll notice that here in the sulfate, I've started off with 2 hydrogens, and in my product I've lost both of those 2 hydrogens. The sulfuric acid has donated the protons. The ammonia, I've started off with NH3, I've ended up with NH4. It's accepted a proton, and therefore it's acting as a base.